Bismillahirrahmanirrahim. Even though the vast majority of regressions being run today are nonsensical, there is one special class which is recognized by econometricians as being spurious or nonsense. So in this lecture, we are going to study this particular special class of regressions and try to understand why these are nonsense regressions. In causal terms, it's very easy to understand one important reason why regressions can be spurious, and that is when both the variables have a common cause. So if z is a cause of x and z is also a cause of y, then any variation in z is transmitted to both x and y, and this leads to an appearance of correlation between the two of them. And especially if there is no causal link between x and y, then a regression of y on x or of x on y will give very strong results and will give the result that one of them appears to be a very strong cause of the other, when in fact there is no causal relationship. So that is what it means to say that a common cause leads to a nonsense regression. To understand this better, we will look at a specific example of one genuine causal relationship and then contrast it with a nonsensical or spurious relationship. One of the most widely used regression equations is the consumption function. In this equation, we take for a starting point the idea that the income is a very strong cause of consumption. We consume out of our income, and to a first approximation, we can take this as a linear relationship, so that the Singaporean consumption is equal to some constant plus some proportion of the Singaporean GDP, or the gross national income. So this is a relationship at the aggregate macro level. Now when we run this regression using WDI, World Bank data on annual GDP and annual consumption in Singapore in local currency units, we get this regression which is portrayed here. The regression has 99.6% R squared, which makes it a very strong regression. The standard interpretation is that 99.6% of the variation in consumption is explained by the GDP. So GDP is a very strong explanatory factor for the consumption. And the constants comes out to be estimated at 4.4, and the marginal propensity to consume, which is the coefficient of the GDP, is 0.486. So this has the interpretation that if you increase the GDP by $100, then $48.6 of this will be consumed. So according to all statistics, this is a fantastically good regression. Of central importance for our purposes is the idea that this regression has a causal interpretation. It says that if we change the GDP by $100, then the consumption will change by $48.6. Now there is some reason to doubt this regression, and that comes out when you look at the regression residuals, which are pictured in the left panel. And you can see that they are very systematic, very patterned. To understand what it means to say that these regression results will have patterns, I have plotted a collection of random residuals on the right hand side. These are just randomly generated residuals, and if you can see them, then they vary up and down, fluctuate, and basically the idea is that by looking at the previous ones, you cannot predict what the next one is going to be like, whether it's going to be positive or negative, whether it's going to be large or small. You cannot predict what's going to happen. As opposed to this, if you look at the first series, the actual regression residuals, by the way, residuals are the difference between the actual value of the consumption and what the regression forecasts as a linear function of GDP. So if you look at these, you can see that there is a very strong pattern to these. Now the reason that this is a problem is that regression is run under the assumption that the errors of regression are random. And so all of the statistics in the regression, the so-called T statistics, F statistics, confidence intervals, p-values, R squared, these are all interpreted under the assumption that the residuals are random. So when they are not random, as is obviously the case, then all of the interpretations are suspect. So what do we conclude by looking at this regression, the consumption function, and thousands of others which have been run in the literature? Well, in this particular case, and mostly when you run a simple Keynesian consumption function, you find that the residuals are not random, so that the regression is not valid. So in particular, it means that the estimate of the causal effect 48.6 in here is not very stable. If you try to fix the problem by adding regressors or by many other methods, this leads to a large number of fluctuations in this constant. And this is basically what a specification search is called. We start with this and we see that it is not working because the residuals are wrong. And then we try to fix it, mostly by adding regressors and by some other strategies which we will discuss, and try to get random residuals so that the regression becomes valid. But when this methodology has been tried, and it has been in place for 50 years now, it doesn't lead to good forecasting performance. And there are a couple of reasons why the regression results that we get after trying to search for a good regression are wrong. One of them is that the causal assumptions behind the regression are wrong. And the other is that the search leads to overfitting. And we will explain these concepts later. So despite the fact that the consumption function for Singapore is problematic because the residuals have patterns, they don't look like random residuals, the relationship is based on a genuine causal relationship between the consumption and the income. Now, to contrast with this, we will look now at a spurious relationship where there is no underlying causal relationship between the variables in question. And so we will look at the regression of Singapore consumption on South African GDP instead of Singaporean. So when we run the regression of Singapore consumption on South African GDP, which is basically nonsensical, we get a result which looks very, very similar to the genuine regression. We have R squared of 96.6%. And both of the coefficients, the constant and the marginal propensity to consume, are very highly significant. And so we might be able to conclude from this that if South African GDP rises by 100 rands, then the Singaporean consumption will go up by $51.7. So actually South African GDP is even a stronger determinant than Singaporean GDP, which doesn't make any sense. So despite the fact that the first regression is based on a genuine causal relationship and the second one is spurious, they show the same statistical patterns. The second regression, which is nonsense, has high R squared, high T statistics, high F statistics. All of the statistical measures for assessing this regression look the same as they do for the first regression. So this is the puzzle, that one relationship is very strong, meaningful, the other one is nonsensical, but how to tell them apart statistically, that is the basic problem of spurious regression. This is a puzzle which has occupied econometricians for many decades, and I have also spent actually a lot of effort. Many of my students have done theses trying to figure out how we can find out that the second equation is not genuine and the first one is. Now in this lecture we will argue that these efforts have failed and we cannot find the difference between genuine and spurious regressions because of one important distinction which I will introduce here. One is I will say that nominal econometrics does not go beyond the names. So if I have of the variable. So if I have variable x and I have variable y and I have data on this, then I don't care what x means, whether x is the rainfall data, or whether the X is the GDP data, or whether X is the demographic data, it's all the same to me. All I care about is the surface, the observations, the data is all that matters, and the real world interpretation does not matter. So when this is the case, this is called nominal econometrics. As opposed to this, real econometrics is when it matters that X is the GDP, and we would think differently or use different methods if X was GDP of Singapore, and we would think differently if it is the GDP of South Africa, because we know that one is causally related and the other one is not. So basically, causality is something which has to do with the real world. I know that the Singaporean GDP is the cause of Singaporean consumption because I know how the real world works and how people in Singapore earn income and how they use this income to purchase consumer goods. And this knowledge of the real world, which goes beyond the numbers that are in the data set, it is this knowledge which tells me that the first regression is genuine. Now, nominal econometrics, as I have defined it, cannot detect or deal with causality because causality is a real world phenomena. It is not there at the level of the names, and that is the main reason why the approaches in conventional econometrics, which is very strongly nominal, why these approaches have failed. Now we are going to discuss three of these approaches in this lecture. So there are three basic approaches to understanding why the second regression tells us that South African GDP is a very strong determinant of Singaporean consumption. One of these approaches says that the problem arises because of missing variables in the regression, and so this is called the omitted variable bias. The second approach says that the two variables have common trends, and that is the cause of the problem. And the third approach says that in regression we should be dealing with stationary variables which don't change in their probability distribution across time. So all three of these we will try and show what this means and how they work and how these try to discriminate between the genuine and the spurious relationship, but ultimately these approaches fail. So according to the missing variables approach, South African GDP comes out as a significant determinant because in the regression of Singaporean consumption, we have not included the Singaporean GDP, which is the most important determinant of Singaporean consumption. So if we have a missing variable, and if we add this variable, then this deceptive relationship will disappear, and we will learn that actually South African GDP does not matter, and the missing variable is the real cause. And basically the explanation is that when the variable is missing, then the included variable acts as a proxy for the variable, so it picks up the influence of the when the two variables are correlated. So the South African GDP is actually acting as in place of the missing variable. So the solution to this problem is to add the missing variable. So here's what happens when we add the missing variables. Here's Singaporean consumption on both Singapore GDP and South African GDP. Surprise, both of these variables come out to be significant. Significant is measured by the t-statistic and the p-value of that t-statistic. So if you look at South African GDP, it comes in with a coefficient of minus 0.103, which has a t-statistics of minus 3.6 and a p-value of 0.001, which is very, very low, meaning that South African GDP is still a very strong negative determinant of GDP. So now this is telling us that an increase in South African GDP will lead to a decrease in Singapore consumption, which doesn't make any sense. If you look at the pattern of residuals, again these residuals don't look at all random, so there is some problem with the regression, but also the regression is giving us the wrong causal information. Actually, this is how econometrics is done. We started with one regression, then we modified it and then we will keep on modifying them. We'll add more regressors, take some out, change the functional form, use logs, use differences, many other tricks that are there in the bag of econometrics to come up with a specification which has both the right causal interpretation and also has the right looking residuals. And this is called specification search. We look for one model after another, adding and subtracting variables until we get what we want. But this has a very different picture from what the students are told. The students are told that we run a regression and we find out the answer. And this is not true. Actually, we keep fitting regression after regression until we get one which matches the answer that we had in our head in the first place. So we don't learn from the data, rather we teach the data what to say. This methodology of econometrics has been recognized by many people. So there is an interesting quote that if you torture the data long enough, it will confess. That is, start with any idea that you have about what is the nature of the causal relationships, and eventually you can find a regression which will support your idea. So now we look at the second solution to the problem of spurious regressions, and this is based on the idea that there is a common trend in both variables. So time is a cause of x and time is also a cause of y. So because of this common factor, the variables show common correlation which is not really genuine. So the standard solution to the common factor is to condition on the common factor. So if we hold time constant, then the correlation caused by the fluctuation of time will not happen. But this doesn't work in time series, because when we hold time constant, there is only one observation at every time period. So there is a second approach, and that is to say that let us try to find out how time affects the variable x. And so that is called estimating the trend. What is the trend in x? And similarly, find out the trend in y, remove the trends by taking the influence of time out of x and take the influence of time out of y. And so now you will have two variables which have been detrended, which don't have the trends. And then if you run a regression of one on the other, then the common factor effect will be eliminated, and you will be able to tell that this is not a genuine relationship between the South African GDP and the Singaporean consumption. So that is the strategy of detrending. And now let's look at how it works. So here's what happens when we try to detrend the Singaporean consumption. Basically, the method to detrend is to run a regression of the Singaporean consumption on time. And when we do that, we get this relationship which has been estimated. Consumption is minus 91 plus 5.775 times t. You look at the picture, you look at the straight line, that's the time trend, and look at the blue line, that's the actual consumption data. You can see that the fit is very bad, and if you look at the regressions, they show very strong patterns with respect to time. So the basic purpose of detrending, which is to get a set of regression residuals which are not related to time, has not been achieved. The regressions are in fact strongly related to time, so they will not be detrended in the sense that we need to run the second regression. So basically detrending fails at the first step. Now this doesn't mean that the process has failed. We can go on and improve it and actually get it to work by adding a quadratic time. So instead of t, we add t squared and maybe t cubed if necessary. And ultimately you can show that this will work, in the sense that the residuals that you get from that relationship will look pretty random, and the time trend will fit very well to the original data set. So mechanical application of this procedure will actually succeed eventually. But there is a problem with this, and that's just that just like the specification search, you keep adding terms until it works, but the underlying relationship is meaningless. It is not really the time trend, it's just an accidental fit. You've forced a fit on the data which doesn't really exist, and this leads to very poor results in practice. So we can conclude that the detrending method did not work, at least in this example, although it does work in some other examples. So the third methodology for dealing with nonsense regressions is to transform the variables to stationary. Now, the concept of stationarity is that the distribution of a variable should not change over time. And a trending variable violates that because the variable keeps increasing. And so its distribution keeps changing with time. So one of the standard ways of achieving stationarity is to look at the difference of the variables or the growth rate of the variables. And often this transformation works to remove the trend in series. So in this example, I will try the percentage growth. And the percentage growth is defined as the log of the current observation divided by the previous observation. And we have discussed this growth rate variable in earlier lectures. So I detrend all three variables, the consumption, the GDP of Singapore, and also the GDP of South Africa by this what's called data transformation. This time, looking at the growth rates, we do get rid of the time trend. If you look at the growth rate of the Singaporean consumption, it fluctuates up and down randomly. And similarly, the growth rate of Singaporean GDP also fluctuates up and down randomly. So the time trend has been removed. So a regression of these two variables should give reasonable results this time. So here's what we get when we regress the Singaporean consumption on Singaporean GDP. And the R squared is 68.4%, which is very high. But notice that it has gone down from 99%. And the reason is that the common trend has been removed here successfully. And so the correlation that was due to the common trend is no longer there. But still, we have a very decent, healthy R squared. And the coefficients are significant. And so we can take 634 as a causal coefficient. If the growth rate of Singapore GDP increases by say 10%, then the growth rate of Singapore consumption should increase by 6.3% according to this equation, if this is valid. Interestingly, this time the residuals are also showing no patterns, and the residuals are, for the first time, really looking random. So we have some reason to trust this relationship, unlike the previous regression relationships. But our main problem was to see if this allows us to differentiate between the genuine causal relationship and the fake or spurious one. And we find that that doesn't work, because when we run the growth rate of Singapore consumption on the growth rate of South African GDP, we still get a strong relationship. This time the R squared is only 30%, it's less, but this is still a fairly decent, a strong relationship. And that is 30% of the variation in Singaporean consumption is explained by South African GDP, which is obviously false. It is not true that South African GDP has such a strong relationship. Similarly, if you look at the T statistics, the coefficient 566 has a very high T statistic of 9 and a very low P value. So the regression is telling us that we can trust that this variable, that it is a strong determinant. And also the residuals don't show any patterns, so the regression is not rejected immediately because of the patterns in residuals. So this transformation to growth rates solves the problem of random residuals, but it does not solve the problem of differentiating between the genuine causal relationship and the fake relationship. So the problem of spurious regression is not solved by transformation to stationarity. And the reason that we know that this second relationship is nonsense is because of our knowledge of the real world. I can say with confidence that South African GDP does not have that strong an effect on Singaporean consumption, because I know how the real world works. So only because of my knowledge of the real world can I say that the second equation is nonsense and the first one is not. But this is not part of knowledge available to nominal econometrics. If you only know the names of the variables, then there is no way you can tell the difference between the first equation and the second equation, the genuine causal equation and the fake spurious nonsense equation. Now, if we transform to stationarity and then we add the missing variable, that does actually solve the problem. And we find that when you run this regression, then the Singaporean growth rate is significant and the South African growth rate is not significant, and the errors are random, and the causal impact coefficient of the Singaporean GDP is a sensible value of 57%, and the coefficient of South African is not significantly different from zero, in the sense that the null hypothesis that it is zero cannot be rejected by the data. So basically you can defend this second equation, and this is how econometrics work. You keep on trying things until you find one that matches your prior causal ideas. That is called that matches our preconceptions. But then we can't say that the regression proves my idea is right, because actually we looked through all the equations to find one which matches. And so that is the basic dilemma of specification searches, that you can't use the regression to say that this regression supports my result, because you looked for one until you found something. And there were thousands of regressions in the middle that did not support your result. So you don't look at them, and you look at only the regression which actually supports, which matches your preconceptions. So to conclude this lecture, we can say that none of the three methods that we discussed is bulletproof. None of them actually always leads to the right results. There are, in the sense that we can't get rid of the problem of nonsense regressions by any one of them in a reliable way. But we can also say, because of long experience with this, that we can always find something which will work by mixing and matching these methods and trying something or the other. We will eventually get to something which supports our causal intuitions and also has random regressors. But because this specification search is basically trying to justify our preconceptions, then the forecasting methods based on these regressions often fail. And the ultimate conclusion that I would like to end with is to say that nominal econometrics does not have any method to discriminate between spurious and genuine causal relationships. And econometricians have been studying this problem of nonsense regressions for decades, and they have failed to find the answer, and they will fail to find the answer because the answer does not exist at the level of nominal econometrics. It can only be found by going beyond the data to the real world relationships which are causal and which are underneath the data.